J'ai l'heure du coup. Ah. Il est où? Il est où?
Well, it's at the hour, so it is. So my name is Karin Oberg, which means I have the honor and pleasure to introduce today's speaker as the advisor of Alexia Simon. Especially, bonjour et bienvenue à la maman d'Alexia et à ses amis. Nous sommes ravis de vous avoir avec nous pour cette défense de thèse. And that roughly exhausts the French that I remember from school. So, so I will continue in English with your permission. So when we think about what this thesis is about and what you're about to enjoy, and I just saw another costume, and this is awesome. I think so laboratory astrochemistry roughly got started around 40 years ago or so. But I think what's really special about Alexia's thesis and what you will see is just how important it is to be willing to design and then execute a lot of experiments. And how that actually getting to explore the parameter space, actually thinking about your error budget, that's needed not just to get to a quantitative understanding of how the chemistry among stars and planets work or when stars and planets are forming, but it's also needed to get the qualitative understanding. One of the things I think Alexia has really helped us do is taking the field from a place where we mainly do exploratory experiments, which were still super important, we still do them, but then really trying to comprehensively understand them. Now, doing that is not easy. It takes a lot of work. And I think Alexia has put in a lot of work. And I think your determination in getting the experiments that you need to actually understand the chemistry behind it is one, I think, of the sort of beautiful highlights of this thesis. I think you've just really helped to set a new bar, both within our group, but also in the field at large. That's something that I'm very proud of being part of this journey. Now, I'm not going to say much more because I want you to get to present what the results of that journey is, but just to say that, how proud I am that we have, of all the work that we have done together and the beautiful results that are coming out of it, and that I am probably as excited as you are to see you present that today. So please, Alexia, take it away.
Really high. I think I'm going to avoid a lot of faces from the crowds. So if I look at my slide, it's not that I want to be impolite. It's just like I'm retaining my tears. But thank you, everyone. Thank you, Karen, for such sweet words. And thank you for everyone for coming here today. And good morning. My name is Alexia Simon. And I'm so excited to share my dissertation today. And what I'm going to talk about, as you might guess, is chemistry in space. Or in other words, my research asks how ices in space record and reshape the chemistry that builds planets. To actually understand the history of our solar system, we have to first consider the environment from which it was born, which starts by what this image shows, a molecular cloud, a mixture of gas and dust that over time will get denser to create a new-born planet, and through millions of years, the formation of potential planets. But an easier way to look at it is through this cartoon, where here we start with a molecular cloud, where simple and maybe more complex molecule forms in, will with time start to condense on itself and then create a new star, where the material from the cloud will start surrounding as a disk, and with some ejection material. That's a process that is really warm with a lot of shocks. That's what we call a protostar. Over time, this material is going to settle in the disk to form what we call a protoplanetary disk. And finally, within this protoplanetary disk, we're going to have planets and planetesimals, like comets, that are going to form. And we're going to keep this cartoon in mind through all the talk. But let's start with the first stage, the molecular cloud. The molecular cloud is mainly composed of gas, but also solid dust grains. But for my research, what I'm actually interested in is ice. Ices are molecules or volatiles that come on the surface of the grain. The grain is composed of silicate and carbon, nanometer scale. And once it freezes out, those molecules, we're going to get our ice. And it's important because it's going to induce a lot of chemistry on that surface. And something amazing, thanks to the James Webb Space Telescope, is that we can observe the ice inventory in some of those stages. And so here, if we look at our cloud, we can actually know what the inventory of the chemistry is in this molecular cloud. And here's a spectra. It's OK if you don't know what it is, but it shows which molecule are present at this first stage. We can have water, CO2, CO, but also methane, and a little bit more complex with methanol. So that gives us a first insights of what is present at the beginning of everything. And then you might wonder, what do we have next? Well, because we just formed a star, the star is going to induce some energetic processes like heating, but also UV irradiation. Thankfully, with the James Webb, we can also look at the ice composition in a class 1 protostar that is here. And here's 2 spectra of it. We see the same molecule that we've seen before in the molecular cloud, but we also notice more complex chemistry that has happened. So we do see some evolution from that stage to the next one. OK, if we go to the next stage, the protoplanetary disk, here we have some setup to do first. Here is a sketch of a protoplanetary disk where we have our star in the middle. And our star is going to set up some temperature gradient, but also UV irradiation. So if your ice has to be present in the protoplanetary disk, we will expect the ice being further away in the disk in the solid phase. And then if that ice gets closer to the star, we're going to get sublimation of it, going from the solid to the gas phase. And that's what we call snowline, the sublimation temperature. And each molecule has a particular temperature for which it goes from the solid to the gas phase. So now we can wonder, what could we know from that stage? Well, we have some ground space observation. So it's different in that case because we cannot observe ice directly, but we can have other information. If we look at the lower panel here, we can map the dust emission in a millimeter continuum. And on the panel above, we can look at molecular line emission. In that particular case, we have CO molecule gas emission. And we can see that it maps the disk, and that can give us insight of those snow lines, so where those molecule goes from potential solid to gas phase. But now you might wonder, OK, what about ice? Ice must undergo some processes as well, since we have energetic processes in the disk. And that's true. There's multiple of them. We can have UV irradiation that could induce some chemical photoprocesses, so formation of molecule or more complex molecule, or photodesorption, going in the gas phase. We can also have some heating of our ice, some atom reaction, atom bombardment for molecular formation, or molecular formation within the ice surface. OK, so now let's look at what the planetary system can give us. In the planetary system, we might form planets, planetesimal, and some of them are comets. Comets are really interesting because the cometary ices present in there preserve the record of the molecular cloud and the disk chemistry, which means that some of the material present of those comets might be the inheritance or the pristine of what happened in the molecular cloud up to the formation of planets. And thanks to some measurements in 67P comet, we know some of this inventory with majority of water, followed with CO2 and CO, other volatiles, or methane, methanol. So now if we go into our general topic, if we want to understand this big story, we start in the molecular cloud where we have grain, and on the surface of this grain, we're creating ices. So that creates the initial abundance, the initial composition of chemistry in the cloud. Through time and through the stages, we're going to have some reprocessing due to energetic processes, up to our planetary system where we could have some preserved chemical inventory. And that's amazing because observation gives us insights on what we could see in different phases. But what we really want to understand is what happened between one stage to the other. What are the processes that happen? But also, if we have an observation of a certain molecule, how do we get the formation of that particular molecule? What is the history of the composition of our planets? Well, that's the question I'm going to try to answer in a certain way. But I divided it by 3 main questions topic. The first one is, how do ice sublimates? For that questions, I'm looking at a particular mechanism, which is called entrapment of more volatile species in less volatile ice matrices like water or CO2, since we saw that's the major components. How do ice form? So how do we actually create more complex molecule? And for that case, I'm looking at a particular molecular formation, which is deuterated methanol. And finally, how do ice evolve under a certain sources of energetic process, which I choose to be UV. And for that topic, I'm looking at a specific ice mixture of 2 components that I'm going to irradiate through UV irradiation and look at what is happening in terms of hydrogen to deuterium exchange. And so these are the 3 chapters of my thesis that I will approach next. But first, I might say the word that you might be like, what the heck is that? What is deuterium? Well, it's interesting. Deuterium is an isotope of hydrogen, which means that it's the same thing, but heavier. Why do we care? We care because deuterium is present in our oceans, for example, which means that we inherited some deuterium somehow, which we need to understand. I mean, it's there. Why not understanding and using it? But something amazing about deuterium is that when the Big Bang happened, the level of deuterium stayed constant and will always stay constant. The only thing that's going to change is the distribution of this deuterium within molecules. And so we can use that in observation to track and map potential pathways, processes, but also formations of molecules. And the motivation behind it is because we do see some change in that case. We call that deuterium to hydrogen ratio. That's how we record how much of deuterium we have in molecule or in stages. And we do see some change in molecules through the stages. So something must happen here, and we can use deuterium to track what is actually happening. And so to answer those questions, there's 3 ways that we can do it. We can do it through observation, theory, and laboratory. All of them are complementary to each other. We need each other. But in my opinion, the coolest way is laboratory. And so I will present one of our experimental setup we have in the Oberg lab. Here is space ketone. And it's mostly made of an ultra-high vacuum chamber that we can see in the middle, surrounded. So that ultra-high vacuum chamber has a pressure of 10 to the minus 10 torr. I think Earth pressure is around the 700 torr. And we're going to be at really cold temperature, 10 Kelvin. And we can do 2 types of analysis. We have an infrared spectroscopy around, and we have a mass spectrometer. The way we actually create those ices in the lab is that everything starts in the gas phase. So we have a gas line where we have our gas molecules that we deposit through a doser until those gas molecules hit the surface of what we call a substrate. The substrate mimics what the grain could be. And when it hits the substrate, we form an ice. And here's a picture of our substrate that mimics the grain. with some ice formation on top of it. That's the whitish that you can see. And as I said, we have two methods to look at it. We have infrared spectrometer that looks at the solid phase. So we look at everything that is the ice and the composition of it. And then the mass spectrometer, which is for the gas phase. So the mass spectrometer is going to record how much of those molecules can we detect when we sublimate and when it gets in the gas phase. Another way to look at it is with this sketch, where we have our substrate or formed ice. We have our two methods of analysis, and then we can apply some energetic processes like UV irradiation and heat. Okay, so I think everyone should be ready to go in my first chapter, which is about a certain mechanism called entrapment of hyper-volatile in cometary CO2 and water ices. And so how amorphous ices, the major one, water and CO2, can trap and keep more hyper-volatile molecule and change potential inventory of chemistry in the stages of star and planet formation. But for that particular process, it takes place in the protoplanetary disk. And the reason is because, as I said earlier, the protoplanetary disk, we have a set temperature gradient, but also some other processes. But here we care about heating. And we know that planets and planetesimal forms from the gas and the ice distribution in this disk. So we have a distribution that is believed from pure components because of the snow lines, that if we have a star forming further away from the star, the composition of the volatile inventory, since it's further away, could have more icy molecules in the core of that planet, while if we get closer to the star, it would have desorbed and would be available more in the atmosphere. But what I'm interested in here is that, is there other processes that can change this distribution between gas and solid composition in the disk? And so for that, I'm looking at entrapment. The way you can think about entrapment is that we have our matrix. So here is a nice water matrix. And you can see that we have some openings. Entrapment is when you mix some water with a hyper-volatile. So the matrix can be water or CO2 in that case. With hyper-volatile, so I'm sorry, it's OH, but think it's carbon monoxide, CO. And it's going to be trapped in the matrix of that ice. So is the desorption of that CO going to stay the same at its normal temperature sublimation, or is the effect of the matrix going to affect the desorption of our hypervolatiles? That's the answer I'm trying to answer. And so if we can entrap, then the ice that should have been present further away in the solid phase, but only in the gas phase closer to the star, will now be available in the solid phase closer to the star to be available in the solid phase for forming planets. And so that will change the predictive models of potential snowline, but also understanding of inventory of planet formation. And that process has been well studied. Multiple experiments have looked at entrapment, mostly in water. And so my goal is to incorporate potential other matrices, like CO2, since CO2 is a major component in space. But also, the most important part is that I want to quantify how much of it I'm entrapping. Because, okay, it's cool, it can happen, but if it's 5%, like, does it really matter? So I really want to quantify how much of this entrapment happens in those hypervolatile. And here's a range of hypervolatile that I choose. And to make the study more complete, I'm looking at different parameters, so thickness of my ice, mixing ratio. So mixing ratio, you can see like, okay, here I have a certain number of water. Am I putting only 1 of CO? Am I putting 10 of this one? Or that could change it. And finally, the temperature deposition. And the way it works is, here are my parameters. I have my ice that I mix with 1 hypervolatile at 1 specific ratio and 1 specific thickness. And so that gives me 1 experiment. So in total, technically, I should have 32 experiments. But as Karen also said really clearly in the introduction, lab work can be tricky, and I end up doing 200 of that one. Yeah, that really teach me a lesson for the next chapters, which unfortunately, apparently, I haven't learned, because the same thing happened. But I guess it's lab work, and thankfully, I love it in the lab. And so a way to look at it for that process is that we have our substrate with our ice, and we're inducing some heating that we can control. So we can control how much of it are we heating and how fast are we heating. And what's important here, one of the measurements that we do, it's called temperature desorption curves. So here you're looking at how many molecules are getting detected in the gas phase through increase of temperature. But here you're not seeing anything, clearly, because our ice is at 10 Kelvin, so everything is a solid phase. But while we increase the temperature, we can observe some desorption. Here, in that case, it's a mixture of water and CO. We see desorption of CO at its normal temperature desorption, so the pure CO desorption line. And then when we get closer to the water desorption, instead of having just water desorption, we actually see that some of the CO has been trapped, and we see its desorption at the same time as water. And so that's how I constrain which quantity has been trapped and which one has not been. And from those curves, I can integrate the area under the curve, and that gives me the efficiency of entrapment for that specific system. And so let's jump right in the results. Here you're looking on the left first at all the mixture I did with CO2 and the hyper-volatile. Each bar plot color corresponds to one specific hyper-volatile. So we have CO2 with argon, methane, nitrogen, and CO. And then we have the same thing for water on the right. Overall, CO2 and water trap efficiently those four hyper-volatile. But remember, I've looked at more conditions, which are more dilution, but also more thicker ices. Don't struggle too much at understanding. We just see an increase with dilution and with thicknesses. And overall, they all trap, they all entrap at pretty good efficiency between 20 to 60%, but with the best entrapment for the thickest and the more dilute ice. So that study taught us that CO2 is a really good trapping agent for this range of hyper-volatile that we have studied, but also that conditions matter since we have better efficiency for thicker ices and more dilute ices. But related to the big picture, now we can potentially understand potential emissions lines, so those molecular lines that we see in the disk that can give us insight on the snow lines, and that can make us understand why, in that particular case, trapped CO could be enhanced in warm disk. But that could also give us insights on the chemical inventory that we could observe in comets. Because now, more ices will be present in the solid phase during planetesimal formation. Okay. Now, chapter 2, where this deuterium starts to come into place. But for that chapter, what I'm interested in is a formation pathway and the formation of methanol, and more specifically deuterated methanol, and how that pathway influenced the formation of the deuterated methanol. So we are going back in the story of our deuterium. Deuterium is, because it's the level is set during Big Bang, is a really good tracer to use. But because I want to back up the story a little more, because here I've just looked at the ices present, but how did the first molecule actually formed? Well, everything happens in the cloud. In the cloud, I said that we have some gas and some icy dust. So far, I was caring about the icy dust, but let's think about the gas a little. Deuterium's present in the gas phase in the cloud, and somehow it has to end up in the surface of our grain if we want to form deuterated molecule on the surface of our grain. And the molecular cloud is the best place for it to happen because it's a cold environment. The way it starts is that we first need to create the first molecule, which is molecular hydrogen. From this molecular hydrogen, we can form H3 plus with a combination of an energetic process, and this happens in a gas phase. From there, our H3 plus can actually combine with the deuterated molecule available in the clouds through an energetic process and exothermic, really efficient, to form H2D plus. This H2D plus is the key component that's going to bring us deuterium on our grain. And the way it happens is we have our H2D plus in the gas phase that combines with an electron, and that's going to dissociate to give us a deuterium atom. The deuterium atom over time is going to land on the surface of our ice and combine, form more complex deuterated molecule. And this pathway is efficient, which makes deuterium enriched molecule in our surface of our grain. And the one I'm going to talk about today is methanol. Here you're looking at methanol, and the reasons why I care about it is because it's the most common complex organic. And here I'm going to present two of the main routes that form methanols, CO hydrogenation sequence. I know, chemical reaction, don't think about it too much. But we have this first pathway, and then we have oxygen insertion. And oxygen insertion is the one I care about. And the motivation behind it is because we have a molecular cloud that over time will form our protostar. But we can actually have different types of protostar. We have low mass protostar, but we also have high mass protostar. And observation has showed the presence of deuterated methanol, which is great, but we want to understand this formation. And the reason is because in the low mass protostar, we form a particular type of deuterated methanol where the deuterium is attached to the carbon, while in the high mass one, the deuterium is going to be on the oxygen. And so what I'm trying to answer is, okay, can my oxygen insertion pathway help us understand which type of deuterated methanol I am forming? But let's look at just the reaction first. Okay, here we have our reaction. Everything starts from an oxygen-bearing molecule, CO2 or O2, that are present in those stages. The UV is going to dissociate our molecule to give us oxygen atoms. We have two types of oxygen atom, one in the ground state, but one that is excited. So the excited one is it's oxygen 1D. It doesn't mean it has deuterium in it. It just means that it got some energy, and it wants to give that energy back. And the way it gives that energy back is by inserting himself in a molecule that, in that case, we care about methane, for the formation of methanol. And that process has been studied and is really efficient. Okay, now let's go in my goal. I want to know how deuterated methanol happens. But to do it, I'm going to simplify that in the lab. And instead of going in more complex methane-bearing, deuterated methane-bearing molecules, I'm just going to do a mixture of CH4 and CD4. And everything starts the same. We have our molecule, we do UV irradiation, we get our oxygen, and then we have our ice mixture of CH4 and CD4, and we look where the oxygen is going to go, and which of these two products, the full deuterated one or the non-deuterated one, is going to be formed or preferred. To start, we're reproducing our normal methanol formation, where we do oxygen in just CH4. Here is a spectra, an infrared spectra of our ice after deposition, where we just see methane. Great. That's what I wanted. That's what I started with. And then I apply some UV radiation that you can see I'm inducing some oxygen insertion in that methane molecules. And here's the spectra after irradiation. And if we zoom in a feature that shows methanol formation, we do form methanol. So yeah, it works. Perfect. We're reproducing results. So what's amazing in the lab is that we can record data point at any time as we want. And so I can record the evolution or the growth of the molecule I'm interested in. So here you're looking at the spectral evolution of methanol formation. And I can integrate the area of that peak to form what we call a formation curve. A formation curve is all those data points over time or over photon fluence, because I'm applying some UV radiation, so I'm giving photons to my ice. And we can extract two information from it. We can have the formation rate, but we can also have abundance. How much of that molecule did I form? But it works. So now what I want to do is that, OK, let's try in my multi-component ice, where I have CH4 and CD4, and I'm doing this oxygen insertion. Well, we have the spectra after deposition, spectra after irradiation. This is my regions where I can see methanol formation. And that's great. I'm forming actually both. Another question is like, how much of each am I forming? So I'm going back to my formation curves. On the top, we have the formation curve for CH3OH, my methanol. And the bottom plot shows my CD3OD, so my deuterated one. You're looking at 3 curves for each because I've done replicates. That's all. From them, we can extract the quantity that I formed. And here's a bar plot showing for each experiment how much of each molecule I formed with the normalized quantity on the y-axis. And so overall, we can notice that the purple bars are higher than the blue one, meaning that I form more of my deuterated one, which means that my oxygen prefers to go in a CD bond than a CH bond. OK, and because we have formed both, it's an efficient process as well. But if we have to think about the big picture again, OK, we know that oxygen likes to go in a CD bond. But remember, I talk about like different type of molecules here. Well, trust me on that one, because we don't have time to go through all of it. But oxygen insertion, and that experiment in particularly, that is the first experiment run in the lab to actually form deuterated methanol, goes in a line of sight where oxygen insertion contributes in the formation of that component. And so that give us insight about, oh, that might be why we see that molecule, or a contribution of it. OK, I'm going to let you digest in just a few seconds before we go to chapter 3, because molecular formation is something. And now we're going to go even more deuterium. For that project, I'm looking at UV processes, so energetic process-induced pathway. For this one, I'm looking at a binary system that is water and a methane molecule, in that case CD4. So you should be used to from the second chapter. And I'm looking how the potential hydrogen from the water can exchange with the deuterium of my methane. The reason is because if we go back to our stages of star and planet formation, we know that our deuterated molecule formed in the molecular cloud. Everything happened over there. But we also know that we have some potential reprocessing in the later stage through the newly born star. But then we also have comets in planetary system that can give us insight of what this chemical inventory is. So is the deuterium or deuterium to hydrogen ratio that we have initially formed in the molecular cloud, is it kept up to the planetary system? As we've seen, there's 2 ways. Well, there's those 2 ways to form the deuterium in space, in the gas phase, in the gas grain. But we've also noticed that when we look at observation of molecule, in that case, it's a protostar. Because water is the main, let me back up a little, just to present the figure first. Here we're looking at the deuterium to hydrogen ratio in some of those molecules. And what's really interesting about it is that the water, which is our first bar, is lower than these other organics. But we know that water is the main component in those regions. So technically, water should be potentially the most deuterated one, and organics then less deuterated since they come later. So we're thinking like, oh, is there actually a process that can induce deuteration of those organics? And that's where my project comes into place, where I'm introducing a third way to actually enhance deuterium in molecules, which is directly within the ice by using photoprocessing. And so here we could induce some hydrogen to deuterium exchange. In the particular case that I'm looking at, it's water and CD4. The way you can think about it is that we have our UV coming to dissociate our bond of OH and CD to then have an exchange of our deuterium and hydrogen. So we have our ice mixture. Yay. We deposit it, and we do UV irradiation, and we look what we have. Well, if we look at the regions where those potential isotopes form, we see that, yeah, they form, and pretty well. We can see the evolution formation of our water isotopes through irradiation, and we see the evolution of our methane isotope through irradiation. And if we can integrate the area of those curves, then we have our formation curves. Just for the sake of time, now what I want to know is that it works, that's great, but what is the mechanism behind it? How can I constrain this mechanism? Everything starts with water dissociation. We can look at the one you feel more comfortable with in that case. But we start with water dissociation to form OH, and this OH is going to attack our CD4 to abstract a deuterium from it to form our isotope water, which is H2O. And then we have a recombination of our CD3 with hydrogen to form our isotope methane. But then we were like, OK, great. Water makes that hydrogen to deuterium exchange. But what about methane? Since we're dissociating methane, can also methane attack the water? And so for that, we actually run another experiment in the lab where we constrain the irradiation of methane. So now we can only dissociate water, and methane is inactive. To do so we run two experiments. The way you can look at it is that here we have a formation curve for what I call a non-filter experiment, which is where I dissociate water and methane, and the filter one where I dissociate only water. We look at the form, and here are the parameters that I can constrain from it. We have the non-filter one where water and methane get dissociated, and here only water get dissociated. On the top panel, we see the formation curves of it. The formation rates. And overall, we just see a decrease of formation efficiency when we add a filter. But what we care about is how much of it am I forming? Is that changing how much of those isotopic products that I'm forming? And the answer is yes. If you look at the gray bar plot, that shows the amount of isotope methane that I'm forming, and that level doesn't change. But in the case of the water one, this level changes, which means that methane plays a role in the mechanism of forming those HD exchange isotopes. And so here, just the road that I'm adding on top of the water attacking my methane, I'm also adding my methane attacking water and enhancing water isotope. It might be a lot, because that's a lot of equations. But what that project has shown is that even though we have our deuterated molecule forming in the molecular cloud, we do have some reprocessing happening that will change the preserved D2H, but not fully. It actually changes it, but we still keep some of our inherited ice from the molecular cloud. So to conclude, if we go back to our main questions, the first one was, how do ice sublimate? To help understanding that question, I looked at a particular mechanism, which is entrapment. And this entrapment in water and CO2, major components in those regions, showed that we can entrap hyper-volatile quite efficiently. For how do ice form? Well, I looked at specifically methanol formation and more deuterated methanol formation. And it has shown that deuterated methanol forms, and it's the first study that showed it, and that oxygen prefers to insert in the CD bond. And finally, how do ice evolve under UV irradiation? We looked at a water to methane ice matrix, and it showed that exchange happens pretty efficiently, but not fully. We do keep off some of the inherited ice, even though we do have some exchange happening. And so here is the main summary results of my 6 years of PhD. And so to accomplish that, of course, I had to have an amazing advisor. I'm really thankful to you because you really believed in me since the moment we met. And you really gave me the chance to really explore laboratory, but by keeping my rhythm. So I'm really thankful for everything you provided me and your support. And I want to thank my committee, Dimitar Sasolov, Michael McCarthy, David Wilder, and my external, Brett Maguire, for every insights, really good questions that I most of the time, oh, I can't look at my mom. But yeah, I think Dimitar's question was always so challenging, but always motivated me to better understand the field every time we had our meetings. So I'm really thankful for every advice you gave me during our meetings. I want to thank our administrator in the CFA. I don't think I would have done such a nice PhD without your help. Like, you helped me in so many ways. Mark, Peg, I'm so thankful for everything you helped me with. Same with Christine. I think I did my first taxes with Christine. Like, she took the time to sit with me for I don't know how many hours to like do my taxes with me. And Sonia for also like supporting our group. And so what would be a lab experiment without an amazing lab group? We have Mahesh, which is our lab manager in the lab. I don't think those 200 experiments would have happened without Mahesh, because he was so reactive to fix any problem we have, but also helping us in the science, motivating us, making sure we're like on the track, we actually do good jobs. And thank you for making that thesis happen, because without the lab, I will never be able to. And then the Oberg lab group, I'm not going to cite all the names, but I'm so thankful to all of you for the many times I train those talks with you, and I do the same introduction for 6 years now. You've seen that project so many times, and so thank you for all of you to be part of that journey. It would have definitely been different without you. And then the astrochemistry group, we are a lot of people. I don't know if you knew that, but we're a lot. And we're such a nice group. I love, yeah, please talk to us. We're great. Astrochemistry is amazing. But thank you to all of you, postdocs, grad students. You always help me making those presentations better. I think even 2 nights ago, I was still training to get more storyline happening, better understanding, better communication, and thank you for making it happen. Thank you to my CFA friends. Honestly, I could say again thank you, but thank you to all of you. CFA is such a great community, and I'm so happy I had the chance to meet all of you. I want to thank all my Boston friends. You made that journey even better through the years, and I'm so happy I had to experience that with such great people. I want to thank a particular part of Harvard, which is Harvard Housing. I had the chance to be part of Harvard Housing as a community advisor, organizing events, and manager, people working in this were such amazing people. Some of them are here today, and definitely built such a nice community and friends through this. And then thank you to my French friends, I guess. Yeah, I'm sorry, that's really old pictures. It's definitely not great for us, but I haven't been home in 2 years now, so definitely need to update most of those pictures. Thank you to all of you for supporting me from so far away, and always having my back. And yeah, my family. I have a big family, I think. From both sides, they've been amazingly supportive to me and especially, yeah, we're a crazy family, but I love them, particularly my mom that is here today. She has been such a great support, and merci beaucoup pour tout. Je crois que j'aurais jamais réussi cette thèse sans toi. And my grandparents, of course, they're my reason that I actually do what I do. They gave me so much strength through the years, and I'm really thankful to them. And my partners, yeah, he made that PhD happen through the last few months. I think he was forcing me to work. Every day was like, have you worked today? How much? Can you do more? So yeah, thank you for always believing in me, pushing me, making this thesis happen, and always giving me the time to go at my rhythm and having so much joy in doing what I do. And to finish on a nice note, my cats. Thank you to my cat to be a silly cat, I guess, and not scratching me, and I guess not destroying all my stuff. As well as my roommate's cat, that is such an asshole, but I love him so much. And my French cat that loves to cuddle, I guess, and sleeps on my face when I go home. And so here are the summary of my research findings to conclude.
Thank you very much for that talk. Are there any questions for Alexia? I see one, please.
You mentioned you did hundreds of experiments. How long does each experiment take?
It depends on what I'm looking for. So the one with 200, thankfully, I could do multiple a day. I was able to do 2 to 3 a day. But for the other projects, those ones were taking a full day. I think at some point I was spending potentially 14 to 16 hours in the lab. Definitely dedication. But I love it. It was, yeah,
So,
6 years, I guess.
So a short experiment is like 6 hours, is that?
Yeah, I guess the shortest maybe took, maybe 4 to 5 hours, up to maybe, 15 hours.
I see another question. Please, Ab.
Yeah, I'm wondering about the substrate that's mimicking the grain. Is it flat or does it mimic the morphology?
No, it is flat. If we had to follow the morphology, that will bring so many new features to the infrared that would make it challenging to understand actually what we form in a solid phase. So we do have a simplified view of it while trying to keep similar conditions and recreate similar conditions.
Please.
In your experiment, I think you mentioned that the chamber is able to get to pressures of 10 to minus 10 torr.
Yeah.
Is that actually the pressure of outer space? So is it mimicking real conditions?
I think so. Actually, yeah. I know astrochemistry is such a different topic. Any question is not a bad question. I'm learning also every day. If you have just general questions, I'm happy to answer too.
I don't see any more. I see one more, please.
Not a science question, but I was wondering what's next for you after the PhD.
Oh, I'm gonna go for a postdoc in University of Virginia in a great. Yeah, I'm gonna join an amazing astrochem group where I'll continue doing some laboratory work and as well as learning some observation. So new challenge coming on the way.
So if there are no more questions here, the committee and Alexia are now going to move into a private session to continue the defense. I would say if you put a hold on your schedule for noon and maybe consider making your way down to the to the lobby around then and be on the lookout for an email to call you to order there. We'll hopefully conclude the defense there around noon. But for now, thank you again so much. Thank you everyone for coming, and it's really great to see you all. Thank you.
Thank you.